Sir, you are muted.
Thanks, Isha. So, yeah, the scouts for today, ID number 56, are you there? Okay, ID number 57, okay, ID number 58. Are you there? ID number 58, 59, 60, okay. Vineet, have you registered yourself on Moodle? Okay, let me just check if I've added you to this group. Vineet, I don't see you in the Moodle website. Have you registered using your DICT email address? As of now, I cannot see you on Moodle. (2020) 01060. I do not see any such user on this particular course registration. Right. So yeah. So in today's Scribe group, you are not there. Okay. So today's group consists of ID numbers 56, 57, 58, 59, 61, and 62. Okay, so 57 is present, 60. Once again, Vineet, so you're not in this particular group. Okay, so I'll add you in some other group perhaps. 56, are you there? 58, 59, 61. Okay, there. All right, so let's get started with course. Right, we are looking at group homomorphisms, right, in the last class. Let's continue with that. And this is the last proposition we discussed in class, or proved in class, basically. Let f be a function from G1 to G2, which is also given to be a homomorphism, okay, between G1 and G2. In that case, f necessarily has to map the identity in G1 to the identity in G2. Okay. Moreover, homomorphism also maps inverses to inverses. Okay, so f maps A inverse to the inverse of f of A. Also, f maps A to the power n to fa to the power n. Okay, and if the order of an element A is n, then the order of fa has to divide n. And then if H is a subgroup of the domain group G1, then f of H is the image of H under F, will also be a subgroup of the group G2. Okay, and similarly, if K is a subgroup of my codomain group G2, and the inverse image of this subgroup K, denoted here by F inverse of K, should also be a subgroup of my domain group G1. Right. I hope inverse image is clear. Does anybody have any doubts here? Okay. I hope I'm audible.
Yes, sir.
Yes, sir.
Okay, thank you. Right, so then let's move on and let's see what is meant by kernel of a homomorphism. Okay, so let F be a homomorphism between the groups G1 and G2. Kernel of F, okay, it's defined simply as those elements of the domain group G1 which gets mapped to the identity in group 2. Okay, so that's the definition. The notation is this ker of F. I think in the textbook, the notation is kern of F. Okay, so it's just a small variation. Okay, this ker is something that we'll also use for the second part of this course. So I thought let me stick with this notation. Okay, so once again, ker of F, where F is a homomorphism between two groups, is the set of elements in the domain such that all of them get mapped to the identity of group 2. Okay, I hope this is clear. Let's look at a few examples from the same homomorphism examples that we saw earlier. So who would tell me the kernel of this homomorphism F? Even what is the kernel of this homomorphism?
Zero.
Zero.
Anything else? Or is it only 0?
Only 0, sir.
Next. Here, what is the kernel?
Sir, here also 0.
Zero.
0 only.
So we will take that. In this case, what would be the kernel?
Nothing. Empty set.
How will it be empty? It cannot be empty, right? That I hope we can see comes from this result. Kernel of F cannot be empty, right?
Yes, yes.
So what is the kernel of this homomorphism? So either this is not a homomorphism.
X greater than 0. All x greater
Positive.
than 0.
So you can see the kernel of F must contain at least one element that comes from first result of the last proposition, but in principle it can contain many more elements. What would be the kernel of the trivial homomorphism?
So it will be the identity of their first group.
No. So what is the trivial homomorphism F from G1 to G2?
G1 itself.
All element.
Yes, whole
G1.
G.
Exactly, right? So trivial homomorphism means that F for every element A in G1, F of A is P2. Okay, so therefore, kernel of this trivial homomorphism will be G1. Okay, so I think maybe the samples are enough. What do you think the kernel is? Like, it's of course a subset of G1. So these are sort of all the kernels, these examples. Do you notice something special about all these subsets of group G1? So the first case, the kernel is just the identity element. Identity element, of course, we know is a trivial subgroup of G1 of any group for that matter. In this case, of course, it's the subgroup of R with plus. This case, also, again, the kernel is just the identity. So identity as a subset of Z plus is again a subgroup. How about this case? All positive real numbers, is that a subgroup of R star with product? One. Is this a subgroup or not? Closure and inverse, right? So when we multiply two positive real numbers, what do you get?
A positive number.
Positive real number, right? So it's closed. How about inverse?
Yes, sir. For every k, 1 by
Yes,
k
sir.
also
Inverse
exists.
is also there.
So if x is a positive real number, 1 by x is its inverse, and 1 by x will also be a positive real number. So this also is a subgroup. And this, of course, by definition, G1 is a subgroup of itself. Right? So, of course, the question here is, for all these examples, the kernel seems to be a subgroup of G1. Is it true in general? This one, another example that I forgot. Okay, maybe let's look at this example as well, and then move on to the general result. So what is the kernel of F in this case? What is the identity element in G2?
It is I.
So it's not I.
It is.
Is
It is 1.
1. Right? So what is the kernel of F?
Sir, it is
In-
I.
No.
Sorry, it
I,
is.
of course, is an element in kernel of F,
Yes.
but is that the only element?
Sir, it are all the elements.
All
except
identities
I,
order
1.
Once again, what is the kernel here?
All matrices having the determinant equal to 1.
Determinant equal to 1.
Right.
Yes.
Equal to plus 1. Okay, and I hope you know that this implies it's not only identity. There are several matrices. Determinant is plus 1. Okay, and this is what is called, by the way, special linear group. I think so. I think it is. If not, I will correct myself in the next. It's denoted by SLNR, which contains all matrices with determinant plus 1. Okay? And as the name itself suggests, it has to be a group. Right? So SLNR is a group in itself with matrix multiplication. So of course, it is also a subgroup of GLNR because the group operation is the same. Right. So again, yet another example where the kernel of a homomorphism seems to be a subgroup. So obvious question is the kernel always a subgroup? And as this proposition says or states, it is always the case. Okay, so if I give you a homomorphism between two groups, G1 and G2, kernel of this homomorphism will always be a subgroup. Okay, can someone help me proving this? So again, we need to show closure and inverse. Quick, who would like to give it a try? Let's take two elements A and B in the kernel of F. Then, what do I need to show in order to show that this is closed?
A dot B.
A and B
AB
also
belongs to kernel.
Right. Show that AB belongs to kernel of F. Now, what does it mean for AB to be in the kernel of F?
So f of AB is equals to identity.
That is what we have to show, right?
Yes, sir.
So how will we show that?
So here f
What
of
is
AB is equals to f of A times f of B. The group operation is of G2. And as A and B belongs to kernel of F, so f of A will be identity of G2 and f of B will also be identity of G2. It will be E2.
So done. Good. Okay, so closure done. Inverse. Again, let us pick some arbitrary element in the kernel of F. Then to
So here
show,
f of A whole inverse is equals to f of A inverse.
right. So we need to
And f
show
of A-
that f of, speak it a little slowly, we need to show this, right? So what is f of A inverse?
It will be identity.
F
Because f
So
of A whole
how?
inverse. Will be
Right.
f of A whole inverse. And f of A will be identity of group 2. And E2 inverse is E2.
Good. Right. So although writing out all these steps in details looks frustrating, appears to be the case, but at least for this course, ensure that you don't skip too many steps. Okay. Of E inverse is in the kernel of F. Twice the kernel of F. Subgroup of G1, right, for any homomorphism. And as we will see, not sure if we'll see that result today, maybe in the next class, but this kernel of F is not just any subgroup, it's a very special kind of a subgroup. Okay. I'm saying special because I have not yet disclosed what is the name for that special property that some subgroups have. But do keep this in mind. Kernel of F is a very special kind of a subgroup. Okay, let's move ahead. Right. So we have seen several examples where the kernel of F contains more than one element. Okay. Now let us try to study the case in general and figure out under what conditions would the kernel of F contain only one element. Okay, it surely cannot be an empty set, okay, because the identity of group 1 definitely will be in the kernel of F. Under what conditions, right, would that be the only element in the kernel? Right. So, as this proposition states, the condition for the kernel of F being a singleton set is that F must be injective. Okay, I hope all of you know what is injective, right? One to one. So once again, can somebody help prove this? And somebody who has not spoken, maybe. I don't want to sort of take names. I want to put some of you in an embarrassing situation, but it would be great to hear from someone who has not spoken.
Sir, first we will, first part is when F is injective, we have to prove kernel of F
Right.
equal to
So
E1.
let F be injective. Then what's the next
Then
step?
identity in G1 always maps to identity in G2.
Right.
So,
So E1 always belongs to the kernel of F.
And F is injective, so no other element will map to identity in G2.
Great. So just give me a minute to write this down while you can think of the proof other way around. Okay? Since F is injective, there does not exist any in G1. And A is different from E1 such that F of A is equal to 2. Okay? Therefore, kernel of F contains only E1. One way. The way around, kernel of F is given to be only E1. And we are supposed to show that F is injective. Yes, go ahead. Who would want to try this? So what does
we
it?
will
Yes,
try proof by contradiction.
okay. Let's say let FA equal to F of B. Right. Then what do we have to show?
A equals B.
Right. So we need not even look at contradiction. Let's try to show that. So let
Sir,
FA equals FB. Then
A and B are element in G1. So according to
yes.
closure property, A dot C will be equal to B.
Okay. Then why do you want that?
And sir, then we will take for we will we know that A dot C equals B. Then F of A dot C will equal to F of B.
Why?
Sir, A dot C is B. Then F of
B
A dot
dot.
C is also F of B.
Okay. That. Okay. Fine. Fine. Yes. Then
Then F of A dot F of C is equals F of B.
then
Now F of A and F of B are same. So it will be identity. F of C is identity, which is contradiction.
right. Okay. This is fine. I think you can avoid using C simply by doing this way. So F of B is an element in group 2, right?
Yes, sir.
Right. So therefore FB inverse is also an element in group 2. I can multiply on the right by FB inverse on both sides. What will I
Yes.
get on the right hand side?
Identity.
E2. And what is F? F is a homomorphism. So this is equal to F of AB inverse. Okay, what does that mean? AB inverse is in the kernel of F. What is known about kernel of F?
It is singleton set with
E1.
identity E1.
Therefore, AB inverse is E1, which means A is equal to B. Right?
Yes, sir.
Okay, go ahead. So this is an interesting property, right? If the kernel of F has only this element, then F is injective. Okay, so basically it means that you cannot have a homomorphism which whose kernel contains only one element, but it may have some other pair of elements mapping to the same elements. Okay, so if kernel of F is even, it basically means that F is injective as far as the identity is concerned. Right? But it cannot be the case that F is injective only for the identity. It has to be injective for all elements. That is how I would interpret this proposition. Okay? You cannot have that only E1 maps to E2 and f of A equals f of B equals some C, where A and B are distinct. This is not possible. This is basically because of the group. Okay, if there is no restriction on F to be a homomorphism, then of course you can have such a mapping, right? So that, let's move ahead and now define.
Sir, I didn't understand how AB inverse equal to E1.
Okay, so what is, if F maps AB inverse to E2, what can we say about AB inverse?
It belongs to kernel of F.
Now, what is kernel of F? What do we know about kernel of F?
Okay. Yes, sir. Yes.
Right? The only element in the kernel is even, so therefore AB inverse has to be even.
Yes.
Right. Now, so we have defined or we have seen properties of a one-to-one homomorphism. Now let us also impose the condition that apart from being one-to-one, what happens if we get a homomorphism which is also onto? Okay, so which means we are looking at homomorphisms which are both one-to-one and onto, or in other words, bijective. Okay, and since there are several nice properties of such homomorphisms, these kinds of homomorphisms deserve a name in themselves. Okay, and the name is isomorphisms. Iso basically means same. Again. Okay, so a homomorphism F between two groups G1 to G2 is said to be an isomorphism if apart from F being a homomorphism, it is also bijective. Okay, so two groups G1 and G2, call them to be isomorphic, okay, which means again in a more strict sense that their operations, their binary group operations or the interrelationship between elements of these two groups is one and the same. Apart from that, what does bijectiveness imply about the number of elements in these two groups?
They should be same.
Equal.
They should be same, right? So it's an even stricter condition for two groups to be isomorphic. Okay, so two groups G1 and G2 are said to be isomorphic if there exists an isomorphism between them. Okay, and this is denoted by the congruence sign. G1 is isomorphic to G2. The definition clear?
Yes, sir.
Yes, sir.
Let's look at examples. So this is basically from the previous example only. Do you think this is a isomorphism?
No, sir.
No. Okay, why?
It is not onto.
Is not onto. Okay, which element in 10Z can you not reach using this F? for every element, let's call it y in 10z, how does any element in 10z look like?
10k where k belongs to z.
10k where k belongs to z. Then what is f of k? Since k is in z, so it is in the domain of f. So what is f of k?
It will be also 10k.
Will be 10k, which in other words is y. So what can we conclude about f? Is it onto? Yes or no?
Yes, sir.
Yes.
Yes, sir. It is on.
F is onto. And how about 1 to 1?
Always 1 to 1.
1 to 1. I'm going to assume you guys can prove this. Therefore, f is bijective. Is it a homomorphism?
Yes, sir.
F is also a homomorphism. That again, I'm assuming you guys can do it. So, f is
Isomorphism.
isomorphism, which means that z is isomorphic to 10z. So, sort of a strange result. One could sort of say that 10z seems to be a subset of z, right? But it still has the same number of elements, right? So it can be off-putting, but it is a subset of an infinite set, which also can be infinite. Okay, so I hope it's not too confusing either. This f is therefore a homomorphism, and therefore z is isomorphic to 10z, and also of course implies z is isomorphic to any nz, okay, for any integer n. Okay. Let's look at this example. Is this f bijective? It is already a homomorphism. We have seen some of the previous slides. Is it bijective? So one way to show bijective implies two things, right? 1 to 1 and on to. In order to show 1 to 1, you can use proposition 20. Okay, all you need to see is what is the kernel of f. If the kernel of f contains only the identity of group 1, then by proposition 20, it is 1 to 1. Okay, and I think we wrote the kernel of f in the previous slide. What is the kernel of this f?
0.
0.
Plus 0. So therefore, f is 1 to 1.
1 to 1.
Onto
Yes,
y,
it is on.
it is on, right? R plus star, then f of natural log of y. Okay, and natural log of y, of course, belong to I. So it's on. We've already shown that this f is a homomorphism, so therefore f is an isomorphism. Right? This in some sense is something we should expect, right? That if f is an isomorphism, which means f is bijective. Okay, if f is bijective, what do we know about such functions, let alone homomorphisms?
It is
Their inverse
invertible,
exists.
and
Invertible. Okay,
inverse function is also by.
right, an inverse function is also bijective. Not only that, if f is also given to be a homomorphism, then f inverse will also be a homomorphism. Okay, that is what this proposition states. How do we show that? So we have to show two things, right? First is F inverse is bijective. How do we show that?
F is bijective, so inverse is also.
Yes.
Okay, can you sort of show both the things, one to one and on to, rather than just using that result? I agree it's not very difficult, but let's try it out.
F has only one image in F inverse, so F inverse also has one image in inverse image one.
No, but you have to show that.
Yes.
So F inverse is, let's try to show that it is one to one. Okay, so what do we mean by F inverse is one to one?
F inverse A
Kernel
equal
is-
to F inverse B, then A is equal to B.
Right. So F inverse is a function from G2 to G1. And so let's take two elements. Let's call them E2, B2 in G2. Right. And let's assume F inverse A2 is equal to F inverse B2. Then how do you show that A2 is equal to B2?
So we take f on both the sides. F of f inverse A2 is equal to f of f inverse B2. And as we know, f is 1, 1. Then
Right. So F inverse A2 equal to F. Oh, but okay, let's do this. Then
sir, f of f inverse will be A2 is equal to B2.
So since F is 1, 1, we can
if
say
F
that
is 1 to 1, then F inverse A2 is equal to F inverse B2, right? That's the only thing you can say. You need to show this.
Sir, instead, if we multiply means that above equation both side by f of b2.
Okay, let's try that out. So what do you want me to multiply?
Both side f of b2. Post.
No, but you cannot. F of B2 is in G2. F inverse A2, F inverse B2 is in G1.
But sir, F inverse X is equals to X from inverse definition.
That is for all the functions. F of f inverse is
Yes, so I'm not saying what we wrote was incorrect, but just want to clarify you cannot multiply by F of E2 here. These are elements in group 1. So the way I would have,
We can write A2 as f of A1 for some
Yes.
A1 belonging to G1.
right. Even B1 in group 1 such that F of C1 is E2 and F of B1 is B2, right? This comes from F being bijective, isn't it? Then I can write F inverse A2 is F of A1. It's F inverse F of B1. Then
F inverse f of A1 will be A1. And F inverse f of B1 will be B1.
Then A1 is equal to B1.
And it is bijective, so it will map to the same value.
It doesn't even need to be bijective, right? Then, because if A1 is equal to B1, then F A1 will be equal to F
Yes,
B1
that's what
because
I
F,
mean.
right.
Since f is bijective, then A1.
No, that's what I'm saying. You don't need F to be bijective.
Oh,
If
yes.
F is a function,
Right.
right? Therefore, F of A1 is equal to f of B1 is basically saying A2 equals B2. Okay, anyways, I think you guys got the idea. On 2 is very easy again. Will you show that? So I want to find, let A1 belongs to G1, right? Then F inverse of FA1 will be equal to
A1.
A1. Therefore, F inverse is on. Okay, that leaves us with one more thing, which is to show that F inverse is a homomorphism. How will you show that? Let me write this to be clear. Let A2, B2 belong to G2. How do we show that F inverse is a homomorphism? What is F inverse A2 to F inverse B2? Anyone? So, how will you show? I mean, what is F inverse A2 into F inverse B2?
A1 times B1.
Okay. So then I have to write here. Let F B1 equals A2, B1 equals B2. Then this would be A1 B1. Then how will this help us? What happens if I apply both, F on both sides? What is this?
F of A1, F of B1.
F of
A1 into F of B1.
Since F is homomorphism.
Yes, because
then help at all?
F of A1 is A2 and F of B1 is B2.
Then
Take F inverse both sides.
good. F inverse E2. F inverse. Okay.
Yes.
This. I hope it's clear to everyone. Not, please ask. Okay, so till now we have defined what is a homomorphism. We have seen if two groups are homomorphic, although I have not defined that term homomorphic, but if there is a homomorphism between group G1 and G2, then there are several special properties that both groups, their elements have to satisfy. Right, the 6 points that we listed as a part of proposition 18. Now, if apart from being a homomorphism, if I can also come up with an isomorphism between two groups, right, then what are the properties that both these two groups have to satisfy? Okay, so that is the next important thing, because this will bring out that if two groups are isomorphic, then what are the common features in both the groups, right? So that way isomorphism is very important. So the first thing, and which is sort of obvious, if I have two groups G1 and G2 which are isomorphic, then order of group 1 and order of group 2 have to be the same. Is that clear to everyone?
Yes.
Yes, sir.
Yes, sir.
Right? Because the isomorphism F from G1 to G2 is bijective. Bijective means same cardinality. Okay. And remember, both the groups need not be finite in size, right? It could stand for infinite groups as well. Okay. Then what else? This is now sort of an interesting property. If one of the group is abelian, then the other group has to be abelian. Right? So this is sort of the first result where you see the importance of isomorphism. If I give you two groups to study, right, rather than studying them separately, right, if you can somehow show that these two are isomorphic, then you can only look at one group. The other group will also have several same properties. One of them is this second point, right, that it will also be abelian. How do we show that? If G1 is abelian, then G2 is abelian. How do we show this? So again, let's just start from two arbitrary elements in G2. Okay, now I think you can finish the proof. Help me do that.
If f of a1 equals to 1.
Okay, so let us just directly look at this product, right? A2, B2. That is what I need to look at, isn't it? In order to show whether the group is abelian or not. So what is it? A2, B2? Sum A1, B1, such that f of A1 is equal to A2, f of B1 is B2. Right? So A2, B2 is nothing but
F of A1 B1.
of B1. This equal to
F of A1
F
B1.
of
A1 B1, which is equal to
F
B1
of
A1.
P1 A1 because G1 is given to be abelian. This is equal to
F
P1
of
F of
B1
B1
F of
A1.
A1.
which is equal to
B2 A2.
B2 A2. So we are done. Now, remember this statement is an if and only if statement, right? So this is first half. But do I need to prove the second half?
No, because inverse function is also isomorphic.
Great. Right. Proposition 21 helps us reduce our workload by half, right? Okay, so what more? G is abelian, G2 is also abelian. If G2 is abelian, G1 is also abelian. Order. Right? What this says is the order of the element and order of the element in the codomain, right, cannot be any different. Do you see why this should be the case? And of course, contrast this with the case of homomorphism. What is the relation between order of A and FA if F is a homomorphism?
Order of
Order
FA
of FA
divides
divided.
order of A.
Right. F is a homomorphism, then order of FA divides order of A. Now, can you give me a one-line proof for this statement? I mean, for this order of A equals order of FA. This thing is already
Since
known, right? See, remember F is an isomorphism, which means F is also a homomorphism. So this thing is already known.
since it is a isomorphism, F is also 1 1. So order
So,
of A. So order of A will be equal to order of F of A.
is that a direct implication?
So since it is isomorphism, so no kernel of F is contain only one element. So if so then order of A will equal to order of.
How?
Sir, in homomorphism, what can happen that for some f of A raised to n less than order of A, it can equal to identity. So that will be order of f of A. But
Right.
in isomorphism, it cannot happen as
Why?
kernel of
That's
f
the
is.
kernel of F. What has this got to do with kernel of F? We are looking at f of A. What is the order of f of A, right? F of A is some element in G2, whereas kernel of F is something in G1. Okay, I'll give you a quick hint. Use proposition 21.
Here order of A will also divide order of F of
Exactly,
A.
right? F is a homomorphism, then order of FA divides order of A. The F inverse is also a homomorphism. So order of A also has to divide order of FA. And when can that happen?
Both are equal.
Both are equal.
Exactly. Write this down. That implies order of A same as order of A. Once again, I'm not saying all your proofs are incorrect, but I think at least in this case, I like the use of proposition 21. That's all. Okay. There is more to it. So isomorphism also preserves the cyclic structure of the groups. Okay, not just commutativity, also the cyclic nature. How do we show this? Again, analogous with the second point, I will just show one half of this. The other half is automatically implied using proposition 21. How do we show this?
Sir, for any element in G1 which is not equals identity, order of that element is uh, order of G1. So
Right. So basically what you're saying is let G1 be the group generated by some element A, which is not the identity. Right. Yes or no?
yes, sir.
Okay. Then
So sir, order of A will be equal to order of G1.
right.
And order of F of A also equal to order of G1. And G2. Okay.
Therefore,
Since all F of A are generator of G2.
to give this. Right. Is it clear to everyone?
Yes, sir.
So G2 will be generated by F of A, G2 has to be cyclic. Okay, so in fact, in this proof, what we have shown is something more than what the statement demands, right? The statement just says that G2 has to be cyclic, but the proof gives you the generator of G2 as well, isn't it? So if A is a generator of G1, then
F of A is generator of G2.
G2, exactly. So we also know how to find the generator of the other group if we know generator of one group. Okay. More result here, and I think this is most obvious. G1 has k elements, each of order n. Okay, then this is of course again an if and only if statement. And G2 also will have k elements of order n. Okay, no less than k and no more than k. That is the importance of this result. Now we will prove this. Okay, can it have less? I mean, can G2 have less than k elements of order n?
No,
Why?
because if A1 to A1 to AK have order n in G1, then F of A1 to F of AK will have order of n in G2.
Right. No. Right. Can I leave this as a homework? Can I not write this here? I think it is simple enough for that. A1 to AK as remember your name. I have k elements of order n in G1. The image of those k elements will also have an order n. So it cannot have fewer than this. How about more than that?
No, it won't have more than k.
Why?
Let F of AJ other than A1 to AK have order n. Then there must exist AJ in G1 other than A1 to AK that has order of n.
So in other words, what are you using?
Prove by contradiction.
Okay, in some sense you're using proposition 21, right?
Yes.
So again, is sort of trying to use proposition 21 wherever possible. Is this clear? I'm not writing the proof, but sort of assuming that you can see the proof. Okay, so try writing the proof yourselves. You cannot see it. Here, any doubts with this? You can see that isomorphism is a much more stronger property between two groups than homomorphism. Homomorphism, in principle, you can have a homomorphism between any groups that you wish, right? Because the trivial homomorphism is, of course, always possible. Okay, but isomorphism is a much more stronger and a stricter relation or function. Okay, and sort of you can see that it preserves a lot of properties between groups. Okay. And using this isomorphism, we can sort of reduce, right, the study of several different examples to study of only one example. So in particular, if G is a cyclic group, right, then rather than studying that particular example that is given to you, we can replace it by looking at only the set of integers or set of integers modulo n, as the case may be. Okay, this is something I hope you recall we have already used this. Right? When we are looking at several examples of cyclic groups, right, at some point in time I said that this Zn is a prototype of any cyclic group. So what I meant then is basically this. Right? Rather than studying all these different examples of cyclic groups that you can come up with, you can only look at Z or Zn as the case may be. Okay, so if G is a cyclic group, if G happens to have an infinite order, then G will be isomorphic to Z. And the group operation here, which is not written explicitly, is of course the addition. Okay. And if G happens to have a finite order, let's say some n, then G will be isomorphic to Zn. Okay. So is the importance of this result understood? Proof is one thing, but it is more important to see the importance of this proposition.
Sir, for any cyclic group, we can relate it with Zn, and we can take same length of Zn. And
exactly.
Yes.
Yes. So, and then I mean Zn in the sense, because integers are something that we have worked with throughout our lives in some sense. So, what this is saying is basically you can go ahead with your favorite example. Okay, that is what this is saying. Okay, so proof. How do I show that G is isomorphic to Zn or Z?
Take a function that will map generator in G to 1.
Right. So since G is cyclic, implies that G will be generated by some element A. And How will I define this?
Sir, we can define f of a raised to k is equals to k.
Of a raised to k equals k. Do I need to sort of do this? Of course, I'm not saying this is wrong. So once I tell you what f does to the generator of the group, and if I say f is a homomorphism, then isn't that enough?
Sir, it will be enough for if we
Right.
define one property.
Exactly. So in some sense, what you're saying, this is equivalent to saying that f of a is 1 and f is a homomorphism.
Yes, sir. Yes, sir. That is also enough. Yes, sir.
And now you have to show that f is an isomorphism, right? You've defined a function, a map between these two groups. Now you have to show that if this particular f that you have come up with is an isomorphism. How will we do that? So, first thing is to show that f is bijective. How will you show that f is bijective? Is it sort of very easy to, do you think this is easy? In that case, I will move ahead. Can I leave this as a homework? Anybody who thinks this will be difficult to prove? Oh, great. Thank you. Then I believe if you don't speak out, then I will assume you can do this. And then let's move on to the next. So again, I emphasize the importance of this result. Right? If you know that you are playing with a cyclic group, then rather than studying what possibly could be a very complicated example, you can just study the set of integers, appropriate set of integers, okay? Because you should know the order of the group and use Zn, where n is the order of that group. Okay, and whatever property that you derive from Zn, as far as you are only using the interrelationship, the same property applies to the original group that is given.
Sir.
Yes.
Sir, here for showing f is a homomorphism, we have to show only that for all a1 and is for a1 into belongs to G, f of a1 plus f of a2 is equals to f of a1 dot a2. Right, sir?
This is what we are supposed to show. See, any element of the group G is of the form a raised to k, right?
Yes, sir. Yes, sir.
So you can take the two arbitrary elements, denote them by a raised to m, a raised to n rather than a1, a2.
Yes, sir. I was asking for any general group, any general homomorphism.
Right. So in that case, let's say a1, a2 are two arbitrary elements of the group. Then you have to show f a1, a2 is equal to f a1, f a2.
Okay, okay, sir. Okay, so then I can do it. Yes, sir.
Okay. In this specific case, it becomes much easier. Okay?
Yes, sir.
Right. So let's move ahead. So now we are going to talk about some special subgroups.
Sir, I have doubt that isomorphism is a property of two groups or a function, because in this proposition there is no function.
Yes, so two groups are said to be isomorphic if there exists an isomorphism between the two groups. Okay, so when I ask you to show that two groups are isomorphic, it is your job to show me that there is an isomorphism between the two groups.
And the same stands for homomorphism?
No, so we, as of now, you can see we have not defined two homomorphic groups simply because it doesn't make sense. Just give me any two groups, I will be able to, I mean, the trivial homomorphism exists, right, between any two groups.
Yes, yes, yes.
So therefore, there is no sense, there are no properties you can derive which the homomorphism will sort of preserve.
Yes.
Got it?
Yes, sir.
Okay. Right. And so I'm sort of changing the order of the contents as compared to the book, because normal subgroups, they are sort of in the book, the order is slightly different. I've chosen this particular order simply because we have discussed this question in, I guess, either a tutorial or in the class itself. Okay, so before we talk and before I define what is a normal subgroup, right, let me pose this question. I hope some of you remember this question. So we have defined cosets, right, left and right cosets. Let H be some subgroup of the group G, right? Then I'm denoting AIH as the left coset of H in G. Okay, there's this question that we were looking at, right? If I multiply two cosets, two left cosets, will I end up with a left coset or not? Right? Do some of you remember that question? So let
Yes, sir.
AH and BH be two left cosets in G. AH into BH is defined, right? How is this defined?
A times H1, B times H2.
Or sum H1, H2 or H1, H2 in H. Okay, this is how okay, when will the product of these two cosets, which is giving you this particular set, the right hand side, when will this also be a left coset? That is the question I want to pose.
When it is abelian.
So that is one condition, but is that the only condition? I'll write it down. When G is abelian, then AH will be equal to what? Will it be equal to a left coset? What will be that left coset?
ABH.
ABH. So, is that the only condition? Right? Or can I look at a weaker condition? Right? Because I may have a non-abelian group. Are we saying that this is an if and only if condition?
No, sir, because if G is abelian, then AH, BH can also write subset.
No, that's fine, but this will also be true, right?
Yes, sir.
If G is abelian, then this is true for sure.
Yes, sir.
If this is true, can you show that G is abelian? Right. So what I'm trying to say is,
No, sir,
what is
it's
the
not double
defining
abelian.
characteristic for the set of left cosets to be closed under the group operation? Okay, and we show that G need not be abelian. Okay, even for a non-abelian group G, this can happen. Okay, what is the condition? Is it always true for any subgroup H?
Sir, is it AH BH equal to CH, where C is not from H or AH or BH but belongs to G?
Are you saying that AH into BH is always a left coset, but the C here may not be equal to AB?
Yes.
Okay, let's see an example.
Not always, but if this happens, then it is.
If this happens means what? Define this. If G is abelian, then surely this is true, right? AH BH will be equal to ABH.
Yes.
Right? But what I'm trying to find out is what is the smallest constraint on either H or on G such that this property that this property is true.
Sir, AHB should also be 1.
Once again,
AHB is always means C for any H in subgroup.
we are saying that this property, this one over here, is true for any H and any G. So product of two left cosets is always a left coset. Is that what you're trying to say? Try to find the left cosets in, let's say, D3 and verify if this property is true. Okay, I realized I am running out of time. Okay, so maybe it makes sense to discuss this in the next class. But as a homework, maybe take these examples. Okay, which one will work, I don't know. Look at the cosets of the two subgroups of D3, right, and maybe also S3, right, and see if this particular property is true. Okay, not this one, this one. Okay, the question that Vandan had asked is this, right? Product of two left cosets, is it a left coset always? Okay, so look at subgroups of D3 or S3, whichever is your favorite one, and try to see if this is true or not. Okay, so this is what we start discussing in the next class on Monday. Fine. I hope the homework is clear to everyone. Right? If G is abelian, no need to verify, and therefore I am picking up examples of non-abelian groups, and the simplest ones are simplest in the sense the number of elements is only 6. Right? So D3 is a nice example to look at. We know it is non-abelian. So take all the subgroups that you know of D3, figure out its cosets. We have, I think, already done that. Okay, so work this equation 1 out. Verify this for all left cosets or right cosets. Okay, and let me know first thing on Monday. Sorry, Tuesday. Thank you. With that, we'll stop.